we're going to start off with the force of gravity. It is an attractive force, so as far as pushing and pulling goes, we'll just say that the object with mass or energy is going to attract anything else with mass or energy. So mass or energy pulling on another mass or energy. So it's purely attractive. It's not one of our contact forces that I was referring to earlier. I'll refer to it as a field force. And what do I mean by that? A field is any space where we can have like a definable physical quantity. In this case, it would be the magnitude of the force. So if you imagine a planet, gravity would pull down in all directions. Now I've projected this onto like a 2D format, but if this was a sphere, what we get is a three-dimensional field. And the way gravity works, the intensity of that mass as it pulls on all of its surroundings, if we imagine a shell around it, and this was like a cross section of the shell. So I'm just taking a cross section of the space around the planet, or whatever this mass is. It's going to be some distance away. We're going to call that distance r. Well, that same mass, if it's pulling on something that is, let's say, 2r away, the way the field would be spread out, the mass is pulling on the entire shell at once. So imagine a bigger shell around this that's just made up of space. So we got this shell of empty space. That mass is being distributed across the surface area of our imaginary shell. So we got our planet here. Here's our imaginary shell. Now we got a bigger shell. Oh, pretend that's a circle. Let's grab one right here. So that mass is acting on a much bigger area. Well, that intensity gets spread out, and because the surface area of a sphere grows at the rate of the radius of the sphere squared, so area 4 pi r squared. So as this goes up, the intensity is getting spread across a much larger area than we would anticipate. And so according to Newton, with his universal law of gravitation, we get that the force of gravity is proportional to the product of the masses. Pretend that's an m. And inversely proportional to the distance between their centers of mass squared. Thanks to a man called Cavendish. Him and many others. we can equate the two sides by adding the gravitational constant. The gravitational constant is, or this is the universal gravitational constant, 6.67 times 10 to the negative 11th. And just to check our units here, we want to end up with newtons. We need to balance out the r squared, the distance, so that would be meters squared on top. We need to balance out the masses, so that would be kilograms squared on bottom in the denominator. And so hopefully right away you can see that gravity has a noticeably weak effect, and that's kind of evident here in the constant. Without a very large mass, or at least a sizable mass and a very small distance, we're not going to see the effects of gravity. In fact, if this distance is small enough, that's when we'll start to see effects due to the electromagnetic force or the strong force. Kind of to give you an idea, if you imagine like I don't know, maybe you got an A on your spelling quiz as a kid, or you drew a really pretty picture for your parents. They might have put it on your fridge with a magnet. Well, we have the entire planet pulling down on your picture, and this itty-bitty magnet is able to keep it on the fridge. That frictional force pulling up on the paper is just as strong as the gravitational force acting because of the Earth. That's a pretty weak force. Okay, so let's go into normal force. Actually, don't want to go into normal force yet. Let's finish up with gravity. Now, according to Einstein, what he said was, because we don't really know we're moving unless we're experiencing an acceleration or we have a frame of reference. We cannot distinguish the field, the gravitational field, from let's say any other force that would be accelerating us at the same rate. And it turns out we can represent the field strength through an acceleration. We call that the acceleration due to gravity, or G. And the field strength is just the ratio between the force of gravity that the mass would have at a given spot on the field. When we're close to the planet, for Earth, that is 9.8 newtons per kilogram. Well, in the previous video, remember I told you 1 newton is a kilogram meter per second per second. So this is 9.8 kilograms meters per second over kilograms, or meters per second squared. So we can see that the gravitational field, we can think of the strength as its ability to accelerate the objects. And that's why I want you to be careful. This is not gravity itself. This is not the force of gravity. This is the acceleration due to the gravity, or due to the gravitational pull.